Good evening, everyone. Welcome to tonight's McDonald Observatory live stream. My name is Saul Rivera. You've probably seen me in a couple of these before. I'm one of the public program specialists here at the observatory. And today I'm joined by Dr. Stella Offner. And Dr. Offner, tell us a bit about yourself.
Hello, everyone. It's my pleasure to join you all today. So I am faculty at UT Austin, and I work on modeling star formation, so trying to understand how stars like our sun form. I use a mixture of computer simulations and artificial learning type machine learning approaches to connect the simulations and the observational data to answer questions about how other stars are forming now, and thus learn about how our own sun might have formed so many billions of years ago.
Ooh, it's going to be so cool. I can't wait to hear more. And for those of you that haven't joined one of these streams before, welcome. We have moderators in the chat. If you have any questions, feel free to drop a question in the chat, and our moderator will answer it or pass along to Stella or I to answer. If you have, this is on both YouTube and Facebook. So if you by chance step away or want to share it to a friend, it will still be available. So you can kind of do that. And Cav to go in. Let's see. And yeah, Cav with Cav, we've talked a little bit from like the slides, and as kind of Dr. Offner has mentioned. So we're talking about really cool topic today about Starbirth and artificial intelligence. We will be trying to get live views. I say trying because the clouds are not that good right now. But fingers crossed that they'll improve on, or at least there'll be enough breaks for us to see something. And with that, Cav, before we go more into the program, just a little bit about where we are. So McDonald Observatory is part of the University of Texas at Austin. So Dr. Offner and I both work with UT. She currently is out there in Austin, a lot more populated than where I am right now, out at the McDonald Observatory in the middle of nowhere. There are actually about 72 people here on site, making the third largest community in the county. Gives you an idea of how remote that is. And I currently am inside one of the domes at our visitor center. We have a visitor center that the public can visit to learn more about kind of the research going on at the observatory and even look through one of the telescopes. The one that we'll be trying to look through tonight is a 16-inch Ricci Crichton telescope. There's more specifications on the telescope and the camera in the description of the video. You can kind of see it a little bit behind me, though it's still kind of dark. Actually, I could probably grab my phone if I can find where I put my phone in the darkness. I do not remember where. Oh, here it is. So you have a bit of a better view. Still a bit difficult. Another reason if you're wondering why I look so weird, the camera I'm using right now is an infrared camera. So that's why I look really weird. I am not possessed. It's just different camera tricks. So you can see me because the dome is dark. Apart from the three screens I have around me illuminating my face, it's pretty dark right now. And yeah, I think with that, we're going to start going. I think if there's anything else I'm missing. Oh, another thing I will add, if for some reason we can't get live views, we do have some pictures taken by this telescope with the same camera, so you can kind of get an idea of how it looked like. We'll say these images I will be showing, if we can get the live view, have a lot longer exposure time than what we would be trying here, but you can still get an idea of how it kind of looks like in the telescope. Now, with that, I pass it back to you.
All right. Thanks, Saul. I'm in my office here, so not so exciting as out in West Texas at the observatory, though I do have a nice view of Austin from my window. So I really hope we're able to see some of these regions later on when the clouds clear. What I'm hoping to do is tell you a little bit of background about how star formation, how stars like our sun might have formed, and then about some of the analysis that I do, and then hopefully look at some of the regions that you can see through the telescope, which is what I'm actually trying to analyze with my machine learning approaches. All right, so here we go. All right, so we did our introductions. So I want to start out by talking about the life cycle of stars. If you tuned in from the live stream a couple of weeks ago, there's going to be a little bit of overlap there. And then I'm going to talk about some different things and show some new things that I didn't talk about there. And of course, I'm happy to take questions about my work and how I can integrate machine learning into learning about astronomy objects. All right, so to give you a big picture, right, zooming way out, we can't have a bird's eye view of our own galaxy, but we can look at other galaxies like Andromeda, which are star-forming galaxies. They're forming stars right now. So by looking at star formation around us, we can try to get a sense for how our own sun formed. So if we could look at our Milky Way, it might look something like this. It's a spiral galaxy. These dark lanes there are dust lanes in the spiral arms. And as those denser regions where most of the star formation is happening, plus some in the center. So if we zoom in a little bit into one of those spiral arms, we'll see an overdense region, which we call a molecular cloud. Astronomers aren't very creative when it comes to naming things. So it's a molecular cloud because it's made of molecules, mostly H2. Sometimes we call these giant molecular clouds because they're relatively large structures. So this is typical nearby region, which is maybe 50 light years across. This image is actually Taurus, which is one of our closest star-forming regions. Now, a region like that one, and we hope I'll see one of those a little bit later, as taken from McDonald. But if we zoom in still further, one of these types of regions would have formed thousands of stars. And we think that our own sun formed in a region like that with thousands of siblings. So one star system like our own would have formed out of an overdensity of dust and gas within this cloud, which we call a dense core. Again, astronomers not so creative. For non-astronomers, this dense core is a misnomer because these dense cores have something like 10 to the 5 particles per centimeter cubed, which is comparable to the lowest vacuum that we can achieve in the lab here on Earth. So by Earth standards, this is not dense at all. It's extremely low density. But relative to interstellar conditions, it's dense, hence the name. So we can zoom in still further. This is an image of an accretion disk taken by ALMA. And so as this core is collapsing, there's a lot of angular momentum. And so as it collapses, it spins faster and faster and forms this very flattened spinning disk. This disk funnels material onto the star and helps the accretion process. So over time, this young star will eat material from the disk, and the stuff that's left over that doesn't make it onto the star, that goes on to form the planetary system around that star. And you can see hints of this in our own solar system, right? So all of the planets are nicely aligned, which is just showing us that our own system had a very nicely well-behaved accretion disk. When that dust and gas goes away, it basically has all of the planets spinning in this same plane orbit, all in the same direction, which is why our system is so orderly. Right? It's inheriting those conditions from the star formation process. All right, so now I want to see if we can see M81. I don't know if that's, you have any images from McDonald?
Not really. So as of right now, it is still quite bright for M81. The cool thing we can actually see, so it's still too bright to see it completely, but the sky's actually dark enough that we actually are able to get the core come into view. So it'd be kind of like a comparison of how it looked like in the telescope with a bright sky. So as you can see, what the telescope's seeing right now looks kind of it's still kind of lots of daylight right now, so they're still capturing a lot of the light. So still, you can't really make out much details of the galaxy, but a bright fuzzy thing in the center, which I can actually zoom in on a little bit. Let's see. I can zoom in more than that. That is the core of the galaxy. So M81 is quite a large galaxy. It's actually about 95,000 light years across, so just a tiny bit smaller than the Milky Way. And the core, the reason it's so bright is, well, a lot of stars are there. And let's see, I'm hearing a beeping noise. I hope that isn't anything bad. But let's see if I can mess with any settings to bring into view, or might be, or this might be a case of maybe we'll circle back to this one later on, see if as the night goes on, it'll be better. But when you do a very long exposure with this telescope, with this camera, you get something more like this. So you can see, you still see a bit of that fuzzy core of the galaxy. So, but you don't see as much of, well, you see a lot more of it now, better yet.
Yeah, so if we could look at our galaxy with a bird's eye view, it would be a spiral galaxy like this one. And one of the characteristics of star-forming regions is they're very cold. So when I say cold, I mean really cold, like 10 Kelvin. So only a few degrees above absolute zero. And that means that they do not emit light frequently or efficiently in the optical. So when we're looking at a galaxy like this one, what we're mostly seeing is not the gas. We're seeing the stars themselves. And so it looks fuzzy because there are just so many stars there emitting light. And so they show up really bright in the optical. But the darker regions, again, they're not empty. What they are is just colder regions that are not emitting light in the optical. So when you're looking at an optical image like this one, you can see where the stars are forming because those are the dark regions, which are not really emitting much light in these wavelengths.
Yeah, so cool. I'm seeing if you get a better view. Oh, such a pretty image. And yes, see people also commenting on the images taken by our colleague Stephen Hummel. Some other little fun facts about the galaxy. If you're wondering how far away it is, it's about 11.8 million light years away from us. So for reference, there are about 6 trillion miles in a light year. So have a fair movies packed for that trip. And and it's usually known with working with another galaxy we call M82. So known as this, another name for M81 is Bode's galaxy, is one that most people know of it. And it's actually very near Ursa Major. So basically not far from the Big Dipper. It's basically on the back of a Great Bear. You can't really see it with the naked eye. Some of these objects aren't that visible to the naked eye. With a very small telescope, will look kind of like a weird smudgy part in the sky. Actually, that's how some astronomers did research way back when. Basically, point telescope one direction, sit down, look through the entire night, and when they saw a weird fuzzy thing, they'll write it down and see what happens. If the weird fuzzy thing moved over several nights, congratulations, it was a comet. If the weird fuzzy thing didn't move, find someone with a bigger telescope because you got no idea what you were just looking at. Which actually is why M81 is known as Messier 81. The astronomer Charles Messier was trying to find comets. Each time he found a comet, a fuzzy star that wasn't a comet, he added to a list, basically not a comet, do not look again list. And it's just number 81 of that list. Yeah, and some other cool little things about M81. As it also has a supermassive black hole at its center, about 70 million solar masses. From we know, a lot of galaxies have a supermassive black hole at the core. And yeah, so like I mentioned, we can see kind of like darker bands is where there's some star formation going on. And it's one of the brightest galaxies in the night sky.
All right. Okay, well, maybe we can come back to a current image of that one, but we'll move on and then hopefully look at some more star-forming regions with a telescope in a little bit. Okay, so coming back to our life cycle, we went from the largest scales, galaxy scales, like we just saw the image, all the way down to the smallest scale disk, which is the accretion disk. But there's actually a lot of things that happen starting from the small scale and going to the large scale. So it turns out that the process of forming stars is very energetic, and stars inject a lot of energy and momentum back into their environment. So, for example, a young accreting star will launch a collimated outflow, which we call a protostellar outflow. This is very high velocity gas that's, instead of making its way onto the star, it's being ejected at very high velocities. And here high is hundreds of kilometers per second. It's very, very high velocity. And these structures can extend quite a long distance. So this one is maybe tens of light years. This beautiful image, it was taken from the James Webb Space Telescope. And James Webb sees very well in the infrared. And of course, these jets are very hot. And so we do see them in optical and infrared light very clearly. Of course, that thing in the center, that dark blob, that is the cold gas, which we will not see in the infrared. And that's why it appears dark in there, right? So it's actually hiding that young star in the center. As we go towards more massive stars, they not only have outflows, they also have winds. So you've probably heard of the solar wind, this very high velocity wind of charged particles. Sometimes they interfere with our satellites. But mostly in comparison to these high mass stars, our own solar wind is incredibly weak. But high mass stars have very powerful winds, and this wind is strong enough that it sweeps up the gas and dust around it and makes this very large bubble. The most massive stars eventually go supernova. So they really disperse all of the dust and gas around them. And so all of that remaining gas that didn't go on to form stars is now completely swept away by the supernova. Those initial conditions are erased. And of course, the supernova also injects those elements formed within the core of the star back into the surroundings. So when we say we're made of stars, it's these very heavy elements that are formed in the centers of stars and then dispersed through these supernovae. So altogether, this forms this cycle of life, right? From this largest scale of the galaxy down to the formation of the star, and then all of this mass and energy getting injected back into the surroundings, including these heavy elements that are so important for life. All right, so now I have observations of M42. So one of these star-forming regions, if we can see it.
Yeah, so we are lucky the clouds cleared out that part. So the camera didn't catch it, but the screen does kind of cheer. But we are able to get a live view. So here's a live view of M42, also known to many as the Orion Nebula. So this is actually honestly one of my favorite things to look at through a telescope with a naked eye. Just as Dr. Offner mentioned, is one of the star-forming regions. It was about 1,300 light years away, so getting to about 8 quadrillion miles away from us. There are 15 zeros in quadrillion, if you're wondering. And it is the closest star-forming region to us. It actually is visible to the naked eye. So to find it, if you're just outside stargazing, look for the constellation of Orion and look for Orion's belt, the 3 stars in a line. Other people have different nicknames for them. I know in actually some parts of Mexico, they know them as the 3 wise men, whichever name some just call it the belt, some just call it the trio. But the 3 stars in line, which are Orion's belt. Underneath the belt, you see what looks like 3 stars in a line, perpendicular to the belt. That is Orion's sword. Now, looking at those 3 stars, you might notice the middle star looks kind of fuzzy compared to the others. That's because the middle star actually is not a star. It's the Orion Nebula. So as I kind of mentioned, some astronomers look for weird fuzzy things in the sky. This was one of them. And someone kind of pointed out, as Beatrice pointed out mentioned in the comments, we can see the trapezium. So kind of in the center, those 4 stars grouped together are nicknamed the trapezium. So actually I can zoom in a little bit so you can get a better view of these 4. And so the trapezium are some stars that are a lot closer to the edge. The Orion Nebula actually contains about 1,000 stars. just that the cloud is so big, so some of the gas is so thick that's blocking out some of the light. So actually, you can actually see there's some darker areas in this view. That's just where the gas is thick enough. It's actually blocking out some of the light. Yeah, it's such a nice view. Oh, and one of the other cool things you can see was actually hovered over the desktop. As it's kind of getting darker and darker, you might be seeing like shades of pink coming in. So that's the hydrogen gas. So these star-forming regions are giant clouds of hydrogen gas, and we can actually see that going on. The reason the nebula is so bright is all the brand new baby stars inside are lining up from the inside out. Some of the stars in this cluster are extremely young. Some, well, not the cluster, in the nebula are extremely young, about 1 million years old, which is a lot for us humans, but not stars. For reference, to these million-year-old stars were people in about the mass of our sun, they basically be like newborn babies in stellar terms. Yeah, it's such a nice view. See, and we're going to pull up a little map, just kind of showing exactly where it is. So you can see it's in the Orion's belt. So just in the sword.
Yeah, so I should mention it's not the closest star-forming region, it's the closest massive star-forming region. So most of the other regions, including maybe some other examples we'll look at today, are forming low-mass stars only. That low-mass is stars like our sun. But the trapezium is actually a group of massive stars, and Orion is the closest region that's forming stars that are 10 times the mass of our sun. And it turns out that low and high mass star formation is a little bit different. As I mentioned, these high mass stars are extremely energetic. They have these very strong winds. They go supernovae. So there's somewhat different processes that come into play once you have a really large region, which is also forming massive stars. So Orion is forming also low mass stars, but it's those massive stars that really dominate. Those are the really bright ones. Those are the ones that are heating the gas the most and making that beautiful nebula really light up there.
Oh, that's so cool. I didn't know that. Thank you.
All right. And if you were able to look at the sky in the infrared, this is what Orion would look like. As I mentioned, the star-forming gas is colder. So when you have a sort of mature cluster that's a few million years old, it has removed a lot of that dust and gas, and so you can see it very nicely in optical light. But before that, a lot of that light is just hidden, it's absorbed, and the gas around it is much, much cooler. And so if you were to look at the sky in infrared, so much, much cooler gas than what we see when we're looking at a star, you would see a lot of very complex, beautiful structure. And this is what it might look like if you could see, with the Spitzer Space Telescope, or if you were able to somehow see in the infrared, you just see all this beautiful nebulosity that's coming from all the dust and the gas in that region. So we'll switch gears just for a little bit to talk about what I do with my research. So in my research, I use computer models to model the process of how stars form. One of the reasons why this is so important is that astrophysics, the star formation process, is not a laboratory process, right? The densities and temperatures are so low, we can't go into the lab and make these kind of conditions. But we can do that with computers. So we can use our computers to model these very extreme conditions and then evolve them forward in time and see what happens for different initial conditions. So the instrument that I use is the Frontera supercomputer at the Texas Advanced Computing Center, which is just down the road from UT Austin. Frontera is one of the top supercomputers in the world. It has more than 450,000 processors. It does a whole ton of different science, not just astrophysics and what I do, but it does biology and protein folding and climate modeling. It's just a really amazing instrument. So I want to share with you a video of a simulation that I ran on Frontera. So Saul has brought up this movie, but what you'll see is that there is, maybe you can pause it for a second so I can tell people what they're going to see. All right, so you'll see right now, you can see there's different colors there. The purple is lower density gas. It's going to move towards orange, you can see now. And once gravity begins to take over and cause the gas to collapse and contract, you'll begin to see white regions. So these are very high density regions. Those white regions are very small. Then there's a separate degree that's being shown with a color, which is yellow and green. This is where the gas is hotter. And so right now you don't see any green gas because this is all cold, but eventually once the stars start forming, you'll see that. And I should note that this is a fly-through time animation. So you'll see the time is going forward, but it's also, there's some flying through that happens. So that rotation is not part of the simulation. That's just the camera looking at the simulation and then zooming in and moving around. At times the movie will start and stop. So you'll see what happens there. All right, now you can start the movie.
All right.
So it starts with 20,000 solar masses of gas. This gas is, you can see there's a lot of structure there. It's very filamentary. And this is because the gas is supersonic. It's very, very highly turbulent. It's moving at very high velocities, kilometers per second. And because the gas is so cold, that means that we get these very strong shock structures, which gives us all this beautiful complexity within the simulation. You can begin to see now that there's some regions that are collapsing. You can see some white dots there. Those are the dense cores. That is where an individual star system will be forming. These are very tiny relative to the whole cloud. And so we're kind of panning around. As those regions collapse, they will form protostars, and those protostars will launch these protostellar outflows. And you can see one of them going off in that direction. As more regions collapse, you'll see more and more of these outflows. There you can see in the top, there's very yellow, right? This is very hot. So now we went from 10 Kelvin to thousands of Kelvin. So there's a huge dynamic range in both temperature and density that you're seeing. You can see there's a lot of messiness with these outflows as well. This is because the stars are interacting with one another. Those two round structures at the top, those are bubbles that were created from massive stars. So as the calculation proceeds, the stars gain mass, and some of them become massive and begin to have these other types of feedback. At this point, you can see sort of in the back that there's some black or darker regions. This is just behind the cloud. So at this point in the movie, some of these stars have just pushed out a lot of the material. And so you can actually see through the cloud. It's no longer being all blocked by all the dust and gas. In the center, there's a very high density of stars. This is forming a star cluster, which hopefully we can look at a couple of star clusters in a few minutes. So now that center region would be visible in the optical. So at that point, looking at that view, you could see this with McDonald. In the early stages, it would be looking very dark just because the gas is remaining cold. But over time, it's heating up. Now we're seeing that beautiful new young star cluster. The star formation is moving towards the sides and is slowing down and slowing down. And then shortly, the first supernova will go off, which happens at around 9 million years after this whole process. There it goes off. That green flash is the radiation that's coming out, which propagates really, really quickly, even before that blast wave propagates away from the supernova. All right. Okay. All right. So now, given that background, I can change gears a little bit to talk about how machine learning comes into focus. I do see a question. I don't know if I'm supposed to be answering questions in the chat or not.
Ooh, well, so this one just came in. Let's see. We can bring it in since it fits the theme. Let's see, from Charlie Ondrej. I hope I pronounced that correctly. Also, hello again. I've seen you on a couple of streams. Can small-scale experiments be conducted in orbit around Earth, since the necessary conditions cannot be created in the lab? Would the benefits be limited?
I think this would be very hard. So once you get away from the Earth and out of the atmosphere, then the densities are quite low. So you are getting to those densities that you would have in these types of regions. But it would be hard to make a sort of lab experiment out of that. One of the ingredients is gravity, and not just that it's there, it's extremely strong. In order for gravity to be that important at such low densities, you need a very, very large experiment. So we could study some of the small scale things that happen, the molecular reactions, for example, which are, in my view, pretty interesting. But a lot of the physics that is important is something that operates on much larger scales than we can make, even if we can get to those low densities. So I think maybe the benefits would be limited.
All right, thank you.
All right.
Yeah. For those of you that might be joining a bit late, again, if you have any questions for us, just feel free to drop them in the chat, and we'll be more than happy to answer them.
All right. So I want to switch gears a little bit and talk about why. What are some challenges of analyzing the observational data and why we need machine learning to help us? There's a couple of big problems. One of them is that actually we have quite a lot of astronomy observations. We have full maps of the sky. This is a piece of the Spitzer Galactic Plane Survey, and I've zoomed out quite a bit. But you can see there's all of this very beautiful complex structure, and you're only looking at a tiny fraction of that survey. If you zoom in and zoom in, you can see some of these beautiful features. These are in the infrared, but that means that you're seeing some warm gas, but not the stars exactly, but the warm gas that's being heated by those stars. And you see these red and yellow regions. Those are shells that are made by these young massive stars or star clusters. They could be produced from the radiation, the heating, or they could be produced from the winds, which are sweeping up and moving the gas into these large bubbles. And just looking by eye, it is really easy to pick them out, but there's a lot of data. And so it is not quite so easy for astronomers, which there aren't that many of us, to go through all this data and then identify all these features. So this brings us to using artificial intelligence. So what if we can make an algorithm that was as good as a human? It was really as good as a human as identifying images and classifying things, but it was much faster, much more efficient. It worked for free. And so that is the lure of artificial intelligence, right? So the term artificial intelligence is pretty old. It goes back to the 1950s. So we define it as the science and engineering of making intelligent machines. So some of you probably think about robots when you hear about artificial intelligence. But when we're talking about astronomy, we usually mean artificial intelligence as algorithms. So these are intelligent algorithms. So ways of analyzing the data that are smart. The other term that we use, you may have heard, is machine learning. This was also coined in the 1950s. It is the field of computer science that gives computers the ability to learn without being explicitly programmed. And often when we say they are learning without being programmed, it means they're learning from the data. So this is really data-driven intelligence, where we're letting the data set the algorithm and set the parameters in a way that is much more efficient and intelligent than if you as a programmer could go in and poke and set them individually. So the way I use AI in my research is to try to connect these computer simulations and models with the observational data. So I want to tell you about one particular machine learning algorithm called a random forest. And this is a method that is really excellent at identifying and sorting objects in a sample. So for example, if you have little images or postage stamps of these bubbles, you could have a random forest help to classify what these objects are. And it works really well in images. A random forest is made of a set of decision trees. And so here's an example. Let's suppose you had an image, this is a bear, and you're going to make a set of decisions that would allow you to determine if this image was a cat or not, right? So your first thing might be, how many tails does it have? All right, well, it doesn't have more than one tail. How many legs? It does have more than 4 legs. How big is it? Right, and so it's not more than 10 kilograms, right? And so at the end of this, you get, it is not a cat, right? On the other hand, if you have this image, right, it has the right number of legs, the right number of tails, and it has the right mass. And so at the end of the decision tree, it would determine, yes, this is a cat. Now, these are sort of made up criteria that you could use to explain your decision to classify these two images. But part of the whole intelligence aspect of these machine learning techniques is that it helps to, it sort of automatically selects where these divisions fall and identifies the path to get from, is it a cat or not to the end. And it's much more abstract than our example here, but it is doing the same kind of thing where it's looking at the data and saying, here are the things I want to find. Is my data like those set of things?
Oh, that's so cool. I've heard of like that train of thought before, but I don't know why I didn't think of it being used in AI, but it makes a lot of sense.
Yeah, so the other key ingredient that we need is training data. In order to train your algorithm, you need to give it a set of data and labels so it learns how to set the parameters within the algorithm. And that means you need a very large set of data for which you know the true answer. Sometimes thousands or millions of examples are required to make a really accurate machine learning method. So we can do that with simulations. And the reason the simulations are so amazing is because we know the right answer, because we have the full physical information. So this is different from just looking at something by eye, where you might not know 100% whether there is a feedback feature in the image or not, whether there is a bubble or not. Here in the simulations, you absolutely know where the bubbles are because you know everything about this data. So what we do is we start from the simulation, then we model the light that's coming out of it. And then we assume that our simulation is a real object emitting light at some distant region in the sky. And then we account for instrumental effects, so the resolution of a given telescope and the amount of noise that we would have to have in that data. And then when we go through that process, we've created a set of mock observations. So a set of training data that's as similar to the real observations as possible. And then we use this wonderful labeled set of data to train our method. And then after that, we can apply it to the real data for which we do not know what the answer is. So this is one outcome of our training and application of our random forest approach. So we trained this algorithm on simulated images on this mock data, and then we applied it to real observational data. And these are 4 bubbles that were previously not classified correctly. In the first version of this, we used only by eye detection, so only labels where people had looked at it and identified things. And this new approach where we use the simulations to add a bunch of data to increase the accuracy. Now we can detect new things that were previously missed. All right, so now is when I hoped those particular bubbles are in the Perseus star forming region, and they're related to two young star clusters, IC 348 and GC 1333. So I was hoping we could take a look at those.
Yep, the weather has been staying on its side, so I do have a live image. So right now we'll start with IC 348. Here's our live view of it. So it is this so far it's been an exposure of about 14 minutes so far, at least stacking wise. So one of the things you might be noticing is you can see kind of like the stars being a big group together, being a young star cluster. But as you can see, was like some cloudiness around some of the stars, that nebulosity of it. It's so pretty. Yeah, this cluster has about, I have written down, about 400 stars, and they're about 2 million years old. So they're little baby stars, they're little babies, and it's about 1,000 light years away from us. Yeah, it's such a nice view. Yeah, and if you were able to get a much longer exposure going on, let's say for a longer period of times in the middle of the night when it's completely dark, and and for those that know to use the software a lot better, like my colleague Stephen Hummel, you can get something more like this. So you can definitely tell it's the same image, but one of the main differences, you can see a lot more of that nebulosity going on, a lot more of that cloudiness. So kind of like the one we have going on, you can see have the same bright stars, just as been a bit flipped, but being realigned, it's really nice views. And all those little stars.
Yeah, it's that remaining gas and dust that makes it really beautiful, because that dust and gas is filtering that starlight and just making this beautiful reflection nebulae. And if you look across these different wave bands, you can get these beautiful colors coming out of that light.
So nice. Yeah, while we enjoy this image from Stephen Hummel, I'm going to move the telescope over to NGC 1333, and we'll give it a little bit of time. Meanwhile, I did see it while we wait for the telescope to point to the target and get some of that light. Some questions did come in. A question came in from Joe. Do you, Stella, spend much time at the McDonald Observatory, or do you primarily request observation data sets?
Yeah, so I am not myself an observer. So that means I don't spend much time at telescopes at all. What I usually do is use archival data. Now, all of these, you know that astronomy is publicly funded. And so one of the ways we give back is by making our data open source and freely available online. And so there are a lot of really extensive archives where you, if you are so interested, can download the data and play around with it yourself. So mostly I use these archival data sets, and often that, there's just a huge amount of data there. People who have requested the time to do those maybe have only done a small amount of science on them. And so there's a huge amount of additional science you can do just by downloading this data and asking new questions about it, which is what I normally am doing.
Thank you. Oh, and I saw a comment from Charlie on Dredge, kind of referring to this cluster, which I do like. A lot like a sunset, not so nice without clouds. It's quite nice. Oh, another question from Joe. Are you using ANN, artificial neural networks, in your AI implementation?
Yes, and that's what I'm going to talk about next. So I'm going to switch gears and talk about a different machine learning approach using neural networks.
All right. Well, we do that. Let's see. We're starting to get our nebula a bit in view. Let's see. It is on the dim side, so see. Do for the time being. See some of the cool facts of IC340. Ooh, that looks really. Oh, I haven't seen that. James of Space Telescope. Ooh, that's so pretty.
Mm-hmm. Yeah, so I should mention both of these images are infrared observations. Again, because this dust and gas is colder, it emits really beautifully in the infrared. What you're seeing in the optical is more a sort of reflected light, just different wavelengths. But the bottom left one is actually showing a very nice bubble, which is one of the ones that we found with our algorithm. So you can see that's, this very characteristic yellow kind of beautiful region. And if you look up to the JWST, you can see, it's actually quite big, and there's a couple of stars in the middle. Yeah, so these are beautiful examples of the kinds of bubbles that we can find with our machine learning approaches. And of course, if you look at it like this, it's very obvious that there's a bubble there. But when you have lots and lots and lots of data, it's just a lot to look through by eye, and it's much more efficient to automate it and use some of these types of machine learning approaches.
Yeah, grad students can only handle so much.
Yeah.
All right, so our live view is almost done. I had gone for at least 60 seconds, but it was still very dim, so we're going for 2 minutes. Just needs about 45 more seconds on that. Oh, meanwhile, let's see a question from Beatrice. What editing software do you astronomers use for astrophotography? I suspect something other than PixInsight, AstroPixel Processor, Affinity Photo, etc. So for the one I'm currently using, so the one I'm using right now tonight is it's the what we call a Sharpcap Pro. So with that, we're able to I can change the exposure times. I can also method the slides to do live stacking. Some of my colleagues do use these a lot more. I know there's some other softwares that get used, but personally, that is not my specialty. So my other colleagues do a lot more on that. But another thing that we might do as well to get more closer to the are lots of filters. So kind of behind the scenes on what I got here. Ooh, the image came into view. Let me just mess with my sliders a bit to get a better color. Actually, this will be a good thing for me to show, so you can see me messing with the little sliders live to get a better view. Actually there looks pretty nice. But let's say I want to increase a little bit of this one. That's a bit too much green. It's a bit too much red. There. I think that's really good. Yeah, we can mess with our sliders and get better views. And also what we do is stacking. So we could just leave it as one single image. If you have a telescope like the one that we're using that has tracking, that's having it move at the same speed the Earth rotates at, you could probably just leave a camera there, leave it attached, have a very long exposure going on for hours on end if you wanted to. Though for a lot of astrophotographers, especially those using it as a hobby, you don't really have a telescope that can do that tracking. The amount that does tracking can really increase the price of the telescope. So instead, you do lots of smaller exposures and then stack them one on top of the other. So probably soon in a little bit, you'll see a little tweak to the image because I am live stacking right now. If we were to keep that going for a long time, you get some more details coming up. Speaking of details, here you can also see a nebulosity going on. But the one I really, really like is kind of the, in this view, kind of the one towards like the upper left, how just, it's like the cloud, the darker gases are like enveloping the star. And you can kind of see it just a little bit poking on up. It's so nice. But if you are able to do that very long exposure and then your filters and settings, you can get something more like this. As you can see, you can still see a bit of that same dark cloud kind of enveloping around one of the stars. But you see a better view of the nebulosity around the main one, which you can see in our first view. Let me just switch on over to that. Ooh, and also, seems we got a satellite flew right through the image.
Must be a Starlink satellite going through.
Probably. Or yeah, if it was like a more recent launch out here, it looks kind of like in movies when they show like a satellite or a spaceship like have like broken apart, like blew up in space and lots of debris. That's how the Starlink satellites look like when they launch in low Earth orbit out here. First time I literally thought it was aliens, and I was like, it might be UFO. I was thinking, what's a satellite? Like, I don't know what it is. Might be a flying saucer. Afterwards, we went in. It's like, oh, it was Starlink satellites. But yeah, so you can see some of that nebulosity going on here, kind of around the different stars. And then once we get the full image, just as we kind of do a little flip to it, you can see that in a lot greater detail. It looks so nice. Actually, you can have it so it takes a bit more of a screen, though sadly we also block a bit of the view. So
That's
nice.
beautiful.
Yeah, and this nebula is about 967 light years away from us, and has an estimate about 150 stars, about a million years old. So very, very, very young stars. Oh, and also kind of a little map of where these are located. They're both near the Perseus constellation. So we also use constellations to help us know where objects are in the sky. Humans way back when used constellations to help tell stories, and we can still use constellations today to basically use as a map of the night sky. And I know we had some like the cool facts about it. Here we are in here. Ooh, that's pretty. Ooh,
Yeah, this is the Spitzer infrared region. You can see some of the same nebulosity up there in the top left. But you also see some additional features that you don't see in optical, particularly these green streaky things in the bottom right. Those are the outflows from the young stars. And there's a Spitzer band that picks those up really nicely.
Ooh, that's nice.
Yeah, and so I think this shows that in any given narrow range of wavelengths, you don't see the full beauty of this. You need to look at a whole range of wavelengths because there's light coming out at a huge range because there's a bunch of different temperatures and densities that are represented here. So you got this beautiful optical, you got the infrared. If we had a radio image, you could also see this in the radio wavelengths. And each of those wavelengths would give you a different view of this region.
So nice. And before you go back, dive into like how we're using AI to analyze these better. Why don't you show the live view again? Now that there's been more stacking, it's been getting darker, you can see even more details now. It's really cool. Almost reminds me kind of like a little lighthouse in the fog, almost. Just zoom in a little bit. Ah, that's nice. It's a very nice view. Ooh. Oh, I heard someone say the nickname of NGC 133 is the Embryo Nebula. Ooh, nice. Didn't know that one. Right. So we should get back to the data. I also see since it's getting darker, we can probably get 81 in view. So I'm going to see if we can get that in view.
All right. Yeah, so we'll switch gears to talk about another machine learning, artificial intelligence approach, and this is deep learning. So deep learning approaches are based upon how the visual cortex works. So as you all know, the human brain is just amazing at processing images. You can look at an image in a fraction of a second and know exactly what it is, who is in the image. Our brain is just amazing at image processing. And so this type of machine learning tries to take the way that our brain works and replicate it using a computer algorithm. So the way our brain works is it has billions of neurons in it. And these neurons are continually passing messages between one another. And depending upon the strength of that chemical signal that's received by the neuron, that neuron will pass it on. That neuron will maybe modify that signal and then pass it on. Or maybe it won't pass it on at all. And so you have this billions of neurons talking to one another through trillions of connections. And so this very complex network encodes a huge amount of information. It encodes that information because we've been feeding it a training set since we were small babies and opened our eyes, we've been getting that training set of images, which have basically trained this huge network in our brains to recognize things very efficiently. And so what we do is we try to replicate this with an algorithm where we have some set of input data, and then we have layers of connections or layers of artificial neurons. And as the image is processed, we basically operate on it. And as we train the network, we feed in, just like we do with our brains, a bunch of different images. And as they pass through the network, it learns the best connections and the weight of the connections between different neurons in the network. So each of these connections that you're seeing, these connections represents a free parameter. And that is what we're training when we pass data or images through the network is learning to set the weights of each of those connections and how important they are. So, right, but instead of feeding cats, we feed astronomy images. And again, the simulations are crucial because we know exactly what is in those images. We have a very detailed set of labels where we know what the true answer should be. And that allows us to set all of the free parameters of our artificial neural network. So the next thing that I wanted to do was not just identify bubbles and outflows in these kind of two-dimensional images, but to identify it in three-dimensional data cubes. So we add another level of dimension, which is the frequency or wavelength of the light. And this makes a spectral cube, a three-dimensional structure. And it turns out it is actually easier to identify this type of feedback in this three-dimensional structure because the wavelength and frequency of the light gives us information about the velocity of the gas, how fast that gas is moving. And things like bubbles and outflows are moving very fast. And so there is some information in that third dimension that's just really important to help us identify them. So what we did was take our simulations and make this mock observations, this three-dimensional data cubes, and then train up a neural network. So we called our network the Convolutional Approach to Structure Identification, CASI-3D. This is what's called a convolutional neural network, hence the convolutional name. So we train it on our mock observations, and then here are three slices through the data. And this is the prediction. Now, these don't probably look like bubbles to you. You might not have identified them. If I flip back and forth, you can see there's some holes there, which are actually being identified correctly by the neural network. But that just goes to show that for this type of data, this three-dimensional data, this is radio data actually, is really messy and is really hard to see these features, even if you're an expert human looking at the data. But our neural network has been trained on thousands and thousands of these data cubes, and it can very efficiently identify these features. So let's see. Did I give you this movie?
You did.
I did. Okay. Yeah. So this is actually a movie, which Saul can show you. It's showing you, it will show you the 3D data. This is a radio observation. And then in that image, the red is the what the neural network has identified as being part of the bubble.
All righty. Ready for me to play the video?
Yes, you can just go ahead and play this one.
All right.
Yeah, so if you see it flat like this, you can see the bubble, but this is the full data. That two dimensions are on the plane of sky, and the third dimension is that velocity or wavelength dimension. You can see there's a lot of very complex structure in the data. And in the middle, there's a kind of a hole. It's not a perfectly round hole or a very clear hole, but there's definitely a hole there, which is the center of that bubble. So inside that hole, there is some kind of star that's heating or has a solar wind, which is pushing away this gas into this shell-like structure. Now, one of the benefits of these neural networks is that they can do at least as well as humans, if not better, because you can think of this as a human who has only looked at this type of data, and they've looked at thousands and thousands of these data cubes. They have looked at nothing else that would confuse them. They are absolute experts on this type of data. And so, if you had such a person, that person would be extremely efficient, but no one wants to look at thousands and thousands of data cubes in the same way. So this type of artificial neural network can perform even better than people, just because we don't have that patience. And it is a savant. It is an absolute expert in this type of data analysis, given the training that we're able to give it.
Ooh. Well, actually, this might be some questions that come in from Joe. In your input layer, do you use one node per pixel, or is the data encoded to reduce the number of nodes?
I'm not sure what you mean by, I see what you mean. So that you're referring to node as one of the neurons? No. So what we do is we feed the data in batches. So each of those neurons is seeing a batch of data. So it doesn't nicely map between this pixel or that pixel. It's seeing a big chunk of the data at any given time.
All right, thank you. And one kind of similar, but also not similar, it seems I was asked a bit ago from Charlie. Are simulations run at a specific wavelength or multiple wavelengths at the same time?
So the simulations are run in real physical space, and they don't know anything about wavelengths. But this is part of the post-processing step, where we assume that simulation is a real object, and that real object has a temperature and a density. And we know from physics how that temperature and density emit light. And so we can do a second calculation on top of the simulation that predicts the amount of light coming out. And then that's where we make the decision about the wavelengths. What wavelengths range are we going to predict that is coming out of this simulated cloud?
All righty.
I think I only have like a couple of more slides, and then it's just all questions. So since we were looking at Orion earlier, the Orion Nebula earlier, this is one of the regions where we have radio data, where we have this spectral data, where we have both position and wavelength or velocity. And so we applied our CASI 3D algorithm to this data, and all of this blue and red, this is the identified feedback from the young stars. The Y's there, those are the young stars marked with the yellow letters. So if we were looking not in the radio, but in the infrared or optical, we would be able to see some of those young stars more directly. But in radio, we only see the cold stuff. So we only see this cold gas and how this feedback from the stars is interacting with it. And so it's these signatures that our CASI 3D is able to pick out really efficiently in a way that we could look at it by eye, but it is very inefficient, and it is not a fun thing to do. So our algorithm is able to identify these features much more efficiently than we otherwise could just by eye. Yeah, so that's the end of my presentation part. I don't know if we're going to cycle back to our galaxy at this point.
Yeah, I say we will. Since now the clouds have gone, it's gone darker, we actually can get a view of M81. So as we admire the view, if you have any questions, please drop them in the chat. Yeah, here we got our live view of M81, the nice spiral galaxy. You can see the arms so nicely. Oh, the question coming from Spudmaster 8000. Do we know what initiates the formation of molecular clouds of hydrogen gas in space to start the star formation?
Yeah, so the gas is just in the galaxy, and galaxies are really energetic places. There's all kinds of things happening in the galaxy at a given time. You can see right here, there's these spiral structures. So there's rotation that's happening and shearing, which is compressing the gas as it's rotating around. And so some of that shearing motion will collect the gas and compress it. Once it gets to enough density, then it will begin to cool and form molecular hydrogen. So that is one way in which you start to get star formation happening. Sometimes you can have gas that's just moving along in the galaxy. Maybe there's some other star formation that's stirring things up and is creating a shock wave, but it starts in motion. All of this, the gas moving and the gas collides. So sometimes you get a collision between the streams of gas, and as part of that collision, it reaches densities that it's enough to begin to cool and form molecular hydrogen. But I think what you should think is that the gas isn't just sitting there quietly, like waiting for something to happen. It's really moving around. Like the star formation is happening, a supernova going off, there's rotation happening. It's a very noisy and complex set of gas, and these conditions just lead to collapse happening at some point. Again, particularly in the spiral arms, where you have that compression that's happening from the shearing motion of the rotation. So there's a lot of things that start the molecular cloud formation. And this is one of the areas of research where people are looking at these clouds, looking at galaxies, and trying to figure out, what is the dominant thing that starts the star formation off. And sometimes it's not totally clear, why star formation is happening, and that's kind of part of the research.
Alrighty. It's a good question. What's getting dark, you can see more and more of the bands. You can see a bit more of the darker parts of the cloud. Let's see. Zooming in.
Yeah, those dark lanes there, that's where the star formation is happening. Those are tracing out the spiral arms, and they're dark because there's a lot of dust and gas in there at higher densities, which means it's a bit colder, so we don't see it in the optical.
Ooh.
Yeah, you can see a lot of beautiful structure, and you can see, I think some of those, so what we're seeing there probably are small young star clusters, those dots. I don't know if those maybe some of them are foreground, but some of the structure within the arms in the galaxy probably are some star clusters.
Yeah, I think so. Yeah, I think but the really bright stars things are just like the foreground ones. But apart from that, I do think like the really bright areas in the arms itself. I think those are some of those regions. Ooh, they look very nice tonight.
Mm-hmm.
See them all around, even towards like the bottom as well. Ooh, there's a lot of them.
Mm-hmm.
Let's see if there are any other questions that have come in. Let's see. I really think I see any. Let's see. Gonna give about a minute or so, see if one comes in.
I think we're past our hour, so people are probably dropping out.
Yeah, that's true. Yeah, and I don't want to keep you longer than need be. Don't want to respect your time. Thank you so much for joining the stream tonight, Dr. Offner. It was super cool getting to like hear and see this up close. Well, up close won't be the word, but get to see it in person, I think, might be the better way to say it. Because when we were giving a presentation, I was out of the country. So I really wanted to see it, but I had really bad internet connections. Like I wasn't able to. This is nice to actually get to learn about more in real time. But yeah, thank you so much for joining in. And again, for those of you joining on the stream, thank you again as well so much for joining in on the stream. If you want to come visit the McDonald Observatory, you totally can. Just go to mcdonaldobservatory.org. Spring break is next week, so if you do not have reservations yet, make them now because it's going to be really busy. And if you want to really watch this live stream or check out any of the others, such as, for example, Dr. Offner did a stream last week as well, talking a bit about this similar subject. If you want to watch that, it's also on our YouTube channel, just McDonald Observatory on YouTube. And you can find this stream and some other ones on Facebook as well as McDonald Observatory on Facebook. And thank y'all so much for joining us.
Yeah,
Have a good night.
This is a lot of fun. I really appreciate you letting me come on here and talk about star formation and AI.
Oh, I really appreciate you wanting to join on in. It's been awesome.
All right. Thank you and take care.
You too. Have a good night.
Bye.